Compare and route LLM replies for clearer metric-driven choices. By the end, you will have a small Python workflow that compares two LLM styles, scores them with a simple metric, and routes new queries to the best choice. You will see how to measure exact match accuracy, add a utility that penalizes verbosity, and inject controlled exploration so you do not get stuck on one model. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. A common pain is choosing which LLM answer to serve in production. Teams often run subjective comparisons or guess based on impressions. A disciplined A/B test with metrics and routing turns that guesswork into repeatable data. Success looks like a consistent rule that routes requests to the model that optimizes a chosen metric, while still exploring alternatives when the signal is uncertain. This is useful for small experiments, low traffic features, or staged rollouts where you want deterministic reproducibility and easy interpretability. Intuitively, we ask two simple questions. First, which model gives the correct or desired content most often? Second, how can we prefer concise, helpful answers over long, rambling ones? We start simple. Measure exact match accuracy on a tiny set of prompts. Then add a length penalty to express a preference for short answers. Finally, schedule occasional exploration so the system can try the other model and learn if preferences change. We will build a tiny end-to-end demo. It will compare two deterministic model functions on a small shared corpus, compute accuracies, add a utility score with a length penalty, and then route new queries with a mix of intent rules and periodic exploration. Here is the first snippet. This snippet calls two tiny models and shows both responses for one query. This snippet creates two minimal functions, named Model A and Model B, that emulate different LLM styles for the same input. The variable Q holds a toy prompt, so the setup is simple and deterministic. We call both functions to obtain outputs A and B, which represent competing candidates in an A/B test. Returning concrete strings avoids randomness and makes the printed list an exact reproducible comparison. The printed list confirms we have two distinct responses ready for evaluation. Now we measure raw correctness on a tiny evaluation set. This example measures exact match accuracy for both models on two prompts. Exact match accuracy means we compare the model answer to the expected answer and count it correct only when text matches exactly. The list named QS holds the prompts, and the dictionary named Gold provides the expected answers. For each model, we compare outputs to Gold and average the matches, then round to 2 decimals for compact display. Because the models and Gold are deterministic, the dictionary shows which model is perfectly correct on this tiny set, making the winner obvious and reproducible. Next, we add a simple content-aware router based on intent keywords. This code routes each prompt to a model using a simple intent rule. The two functions keep producing deterministic outputs, but now we introduce routing logic based on content. The list named QS contains a math task and a knowledge task, and we treat the presence of the word cap as a signal for descriptive responses. The list comprehension builds picks by sending capital-style queries to Model B and others to Model A. This shows a basic, content-aware router that differs from pure accuracy scoring and demonstrates how simple rules can improve perceived fit between query type and model style. Now we combine scoring and a length penalty to prefer concise correctness. This snippet scores models with accuracy plus a length penalty to route picks. We keep the same deterministic models and Gold answers, but now compute a utility score S. The utility returns 1 when the response contains the Gold text and then subtracts 0.2 times the response length to discourage verbosity. For each prompt, we compare scores and choose the higher one, producing a list of selections. Increasing the point 2 weight favors shorter answers and can flip choices away from verbose outputs. Decreasing it tolerates longer responses. The printed counts show how a length penalty shifts selections toward tighter replies. Finally, we add scheduled exploration, so the router sometimes tries the other option. This example adds periodic exploration to the heuristic router. The list named QS reuses the math and capital prompts, and the variable K controls how often we explore model B regardless of the rule. Using an index, we send every kth request to model B, while other requests follow the intent heuristic that routes capital queries to B and others to A. This creates a tiny bandit-style policy that balances exploitation with scheduled exploration. Smaller K increases exploration frequency and gives the system more evidence about the alternative. Recap in 3 crisp points. What it is: a small Python pattern that compares 2 deterministic LLM styles, scores them with exact match accuracy, and routes requests based on utility. When to use it: early experiments, low-risk routing, or when you want reproducible model selection before deploying larger A/B tests. One caveat: tiny deterministic datasets can hide real-world variability. So do not assume these rules generalize without more traffic or randomized trials. Next step, scale the same pipeline by adding timing and accuracy checks across a larger corpus. Or swap the length penalty for a semantic quality score to see how routing changes. Adjust the penalty weight and exploration frequency to tune bias versus variance in the router. If practical AI engineering helps you make reliable systems, subscribe and watch the AI engineering videos.